Alright, so in this video I'm gonna be explaining another important article with the title Featured Graph Coarsening with Similarity Guarantees. This ICML paper in 2023. Graph coarsening is a dimensionality reduction technique that aims to learn a smaller tractable graph while preserving the properties of the original input graph. However, many real-world graphs also have features or context associated with each node. The existing graph coarsening methods do not consider the node features and rely solely on a graph matrix to coarsen graphs. However, some recent deep learning-based graph coarsening methods are designed for specific tasks considering both node features and graph matrix. In this paper, we introduce a novel optimization-based framework for graph coarsening that takes both the graph matrix and the node features as the input and jointly learns the coarsened graph matrix and the coarsened featured matrix while ensuring desired properties. So ensuring desired properties so to the best of our knowledge, this is the first work that they do such thing. So the goal of graph coarsening is just to construct an appropriate sparser. So from node V, we have a smaller number of nodes, V tilde. From edges, we have therefore smaller induced number of edges. Similarly for W and X. So these are the edge weights that becomes W tilde, and X is just the features that becomes X tilde. So the Laplacian matrices L and L sub C, feature matrices X and X tilde, and the coarsening matrix P together satisfy these properties. And C here is the tall matrix, which is a pseudo-inverse of P. So what is the entries of this P matrix? So each entry is a Pij that indicates the J's node of G is mapped to the I supernode of G sub C. And so the non-zero elements of C implies that I's node of G is mapped to the J supernode of G sub C. So the loading matrix belongs to this set. And C sub I, C sub J, they represent I's and J's column of loading matrix. So this is a toy example. You see the featured graph coarsening. The spectral similarity is shown by calculating relative eigenerror. The existing graph coarsening or summarization methods are not designed to consider the node features and solely rely on graph matrix for learning a simpler graph. So the Dirichlet energy is used for quantifying smoothness of graph signals that you see here. When only the feature matrix associated with an undirected graph is given, then a suitable graph satisfying smooth property can be obtained by solving this optimization problem. So S sub L, because L could be anything in S sub L is the set of Laplacian matrices. And so the proposed method for coarsening is like this. We minimize this subject to that C is greater than 0, and this is L sub C. L and X are the given Laplacian and the feature matrix of a large connected graph. But this X tilde and L sub C are the feature matrix and Laplacian of the learned coarsened graph. So the trace of X transpose LX should be minimized. And also the G of C. Because G of C is a regularizer that ensures the mapping such that one node does not get mapped to two different supernodes. And introducing a quadratic penalty for X, we aim to solve this optimization problem. So the resulting optimization problem is a multi-block non-convex. We develop efficient optimization methods based on block majorization minimization framework. So they implemented different for different data sets like Cora, CiteSeer that have high homophily. PubMed has high homophily. Also COCS, and they didn't do it for physics, they did it for CS. These are very high accuracy, and they have I've seen different papers they are about 95% accuracy. I myself tried for physics, for example, 96%, but some of data sets are harder. Like it did not mention in this table, like the one for heterophilous graph, like Squirrel, very hard data set. Chameleon. This is very. Both of them are very heterophilous. State of the art is 45%. This one maybe 49%. Very low. State of the art is very low. So the featured graph coarsening is formulated as a multi-block non-convex optimization problem.